It is my pleasure and honor to introduce Ahmed, Professor Ahmed Ennaoui, a figure well known to all of us as the general chair of this conference. He truly need no introduction, and I will not go into the details of his biography. However, I would like to emphasize one key aspect: his career as a teacher and as a researcher is exceptionally rich, marked by outstanding contribution to high-level scientific research. He has worked in some of the world's most prestigious research centers and universities in Germany, France, Japan, and Morocco, Qatar also. Beyond his research, Professor Ennaoui is deeply committed to the training of young scientists and to promoting scientific culture through the organization of high-level international conferences like this one. For all of this, I would like to sincerely thank him and express my deep gratitude for his remarkable contribution to scientific research in general and to the advancement of research in Morocco in particular. Thank you, Ahmed, for all you have done and you done for Morocco and for young researchers. The talk of the tutorial of Professor Ahmed Ennaoui today is on advanced electrochemical solar energy conversion to green hydrogen and carbon dioxide reduction, learning from the nature. The floor is yours, Ahmed.
Thank you very much, Professor Binyus, for this nice introduction. My name is Ahmed Ennaoui. I want to go through a very important topic, which is the production of hydrogen. I will talk less about the dioxide reduction, but we will, of course, do some think about it. I think it's very important. I will see. Okay, first of all, we will manage a certificate for young student or young attendee, and that's one issue. And now, this topic of hydrogen, green hydrogen, or the reduction of CO2 is very important because it's just the topic of today, and the whole world is working on it. And I just show you here some, for introduction, how actually the situation. So most of the production of hydrogen is through the reforming natural gas. Some of them are from hydrocarbon partial oxidation or coal gasification. So you see here number 49% for forming natural gas, 29% for hydrocarbon partial oxidation, 18% for coal gasification. So it's all these methods are highly producing CO2. More importantly, also after, if you use the hydrogen, there are some oil, refining, methanol production, ammonia production. Also, they have dealing with CO2 also. So it's a big problem. And I just resume here technology, process, and the reaction involved. And you see here that stream methane reforming, which make a lot of CO2. You see it here as 49%. And also coal gasification here, which make a lot of CO2, 18%. And of course, the solution is the water splitting. Here, the third one, where you just produce, you just split water into hydrogen and oxygen, and there is nothing else. So now, if for the energy transition, if we stay as business as usual, the scenario as business as usual, where actually we have 22 billion of ton of CO2, we go straight ahead to the catastrophe, and we will have 42.808. That's the projection. The second possibility, you stay as we are, for example. We switch to less pollution fuel. That's the second possibility. And also this possibility is not really interesting for us. The third possibility, which is interesting, is to cut CO2 emission. And to cut CO2 emission mean we have to use the CCUS technology. This means carbon capture and storing and use. That's yesterday you have heard a talk of Yusuf from University Muhammad Sis. He talked about all this process. So that's the best way, that we have to stop carbon-based technologies, and meanwhile we have to capture the CO2 in the air with this new technology. And that's the solution if we have to go down and to have to keep what people talk about, 1.5 degrees Celsius, and to avoid the climate change. Okay, so telling that, I will start my talk about the water splitting. So I will give you a lot of background for people, the chemists, they don't know about physics, or physicists, they don't know about chemistry. So, and this is maybe new for you, the semiconductor electrolyte junction. So maybe physicists didn't know the semiconductor solid junction, but they don't know semiconductor electrolyte. So they will learn today a lot. And then, most importantly, I will talk about electrochemical measurement. That's what is very important. Okay, let's see now this picture here. That's the splitting of water. You have two molecules of water, liquid. You split it into 2 hydrogen gas and 1 oxygen gas. And you need energy. The energy from thermodynamics is called free energy. And there are many possibilities to do it. But the best one is to find a way to split this reaction, this chemical reaction, into 2 half reaction, what we call half redox reaction. 1 for hydrogen and 1 for oxygen. And this we can do it in a electrolyzer. You see here 2 electrodes. 1 electrode I choose as semiconductor, and 1 I choose as metal. And of course, this metal has to be noble and has to be not very stable, etc. And the semiconductor has to have some properties. We will talk about all this stuff afterward. And from this, with this idea, which is known since hundreds of thousands of years, we can split first this reaction into 2 reactions, 1 for the cathode and 1 for the anode. And we can produce, for example, in acidic medium, where you have a lot of H+, we can split water into, first we have a proton, and this proton can travel a membrane. I don't make it here for simplicity, and then it can be the proton H plus can get electron in the cathode. We will talk about all this in detail. So it's known. You can go to Google and you can find the enthalpy change for this reaction, which is about 2845.8 kilojoule per mole. It's a lot. But you know there is a relation between free energy, enthalpy, and entropy. I think thermodynamic, even if you are chemist or electrochemist or physicist, you know this relationship. So we know everything about the thermodynamic of water splitting. We know the numbers here, the entropy. We know the thermal energy, which is the T delta S here, and we can calculate the change in Gibbs energy, which is 237.1 kilojoule per mole. And this is what we need to make splitting of water. So if we continue the thermodynamic and we know exactly how much electrons are exchanged in this reaction, we can find this number here, 1.23 volt. So we need to split water, the minimum of voltage we need to cut water into hydrogen and oxygen is 1.23 volt, which is, I make it here for fantasy minus delta G over 2F NF in order to split water into hydrogen. And this we can do it with in photoelectrochemistry, with photoelectrochemical solar cell. So 1 mole of liquid to produce 1 mole of gas require a theoretical total energy of 285.8 kilojoule, including the 237 kilojoule of electricity and 48.7 kilojoule of heat. So the thermodynamic, the reversible voltage is here. So this is, of course, we can develop a lot in this slide here, but let's go a little bit more. First of all, I want you to understand that there is a possibility to talk about, as we talk in solid, we can say is density of state in a solid, and quantum mechanics can resolve this problem. We can also talk about density of state in a liquid, in the electrolyte, and we can talk about free donor and acceptor in the electrolyte. And we can also make some mathematics for the donor and acceptor. And we can also define the redox potential for the electrolyte. And we can choose 2 scales. The scale of electrochemist, which is related to the electrode in the reference electrode, and the scale of physicist, a solid state physicist, which is related to the vacuum. Okay. We take 1 electron and we take it to the vacuum, and then we measure the kinetic energy of this electron, and you can know exactly the material you have. In electrochemist, they use potentiostat. We will talk about it afterward. That's one thing. So now you have one information that we can talk about density of state in the electrolyte. And of course, we have a contact between a solid, which is the semiconductor, and the liquid. So in the interface of the solid, the 2 hydrogen from water will take an electron from the solid and produce hydrogen. And here is the point. You cannot do it easily, and more difficult with oxygen. With hydrogen, it's less. But you have both of them. You have 2 half reaction. So there are a lot of theory here to understand First of all, how it's worked, that you have an oxidized species can take one electron to give a reduced species. The oxidation is you lose electron. The reduction, you gain electron, okay? So you have also, you can define, if you know the concentration in your solution, you can define this redox system here, the value of the redox. And of course, we can mathematically define the density in the electrolyte, as I show you here. So you don't need to know more about this. Now, let's go a little bit more in the detail. Now you know two scale, the electrochemical scale and the solid state scale. You know that there is a zero of the electrochemical scale, which can be this reaction here. We can construct, for example, an electrode called saturated hydrogen electrode, where the potential, we can take it as 0. And then if you go down until 1.23, which is the thermodynamic, minus G delta G over NF, that's the reaction to produce oxygen, the other half reaction, because between the two there is only 1.22 volt. So, and all this we can find the equivalent in the electrochemical scale and solid state scale. I give you this for pH 0, for acidic solution with pH equals 0. But we can see this diagram here, what I show you here, for every pH. For example, you can start from 0 pH and you go from 0 pH to 14 pH. And it's still always, there is a plot here, a slope of 0.06 per pH unit here, and you still conserve always this 1.23 volt, except that there is a change in the scale, in the electrochemical scale. You see it here. For example, if you are in basic solution, the oxygen production occur in minus 0.5 something, and the hydrogen production occur in not in 0, but in 0.5 something. That's the only difference. So everything is known. The density of state in the electrolyte is also known. Okay. Everything I wrote here, I made the reference, so you can always go to the reference to know more detail. I talked to you about the water splitting, the formation. You take water and you split it into hydrogen, oxygen. But the nature is very beautiful and can also allow you to take hydrogen and oxygen and make it together and to get your electricity back. That's what we call a fuel cell. So the fuel cell is working as opposite compared to the electrolysis. Okay? Electrolysis, you split water into hydrogen, oxygen, and fuel cell, you make hydrogen and oxygen together, and you produce electricity. That's what you see here in this animation. So you bring hydrogen, you bring oxygen from air, and there is a possibility by catalysis in these two electrodes here. It's always two electrodes. And you can see here that we call anode minus and the cathode plus. Is exactly the opposite of what we have for water. And there's a membrane here, and you see that you will have hydrogen will be split into 2 H plus and 2 electron. That's the opposite of what you have seen in the electrolyzer. And in the other electrode, you have oxygen will take the H plus, which is coming through the membrane, and you will produce as byproduct water, not CO2. And therefore, this is this kind of transformation where you make hydrogen, oxygen together to produce electricity Yeah, people now working on technology to have an electric car or hydrogen car, and you can use this electricity. You can have in your car hydrogen tank and oxygen tank, or oxygen from air, and you can produce electricity, and your car can be autonomous for some time. And that is a technology where actually people work about in this topic. So proton exchange membrane fuel cell, hydrogen atom, electron and proton are separated at the anode. Proton exchange membrane select the proton to move through it. The membrane is selecting only H plus, so if there is any other stuff, it will not go through. And either H2O, water, is the only byproduct. That's only what you have to take away from this, what I have says here. So it's very important. Here also we can do some thermodynamic. Also, you can see here that the enthalpy is the difference between the heat and the work, W. That's the thermodynamic, what you can learn in the first year at the university. If this entropy is negative, the heat is liberated and the reaction occurs spontaneously. So in the case of water splitting, it's not spontaneous. But here, the opposite is spontaneous. That's make the nature very, very beautiful. And you can see how it's work here. You bring some entropy, and you get some work. So you give something and you get something. And that's how it works. And there is an exchange of heat. So this system, if people want to go to the technology and to make fuel cell, they have to think about the heat, how to get rid of the heat, because there is some heat to be dissipated. Okay. Sorry, I have to maybe to go back. Great. So let's see now a little bit more detail. If we make a lot of calculation here, which is very simple, I'm not going to go through. I just want to give you exactly the same relationship like before. When we made water splitting, we need minus 1.23 volt. Now we need plus 2.23 volt. Or without need, we get 1.23 volt. So water splitting, in order to split water into oxygen and hydrogen, you have to give some free energy, which is equivalent to 1.23 volt. Here, when you put hydrogen and oxygen together, you will produce this 1.23 volt. Okay? So now let's go a little bit further. We talked about the thermodynamic aspect. So the thermodynamic tells us that water splitting need only 1.23 volt. But in the reality, there are a lot of barriers when you give this 1.3 volt. There are a lot of conditions. And these conditions, if you are working on the lab and you have people making theory like Professor Benus, they predict this delta G, this free energy, and which material can be selected to have a photoelectrochemical solar cell. You have to go back to the Mendeleev table, and the Mendeleev table you know it very well. So it's a question of understanding every element here. Most of the element what are very important for the photoelectrochemical solar cell are here are the transition element, what they are here in blue. When you take a transition element or a combination of transition element, you can have easily the water splitting, what we call a catalyst. And this is one of the most big problems. When you talk about catalyst, you are not talking about thermodynamic, you are talking about kinetic. You will improve the exchange of electron and the velocity of exchange or the kinetic of exchange of electron at the interface between the solid, the semiconductor, and the electrolyte. And that's another point where chemists, theory and experiment have to work together. Of course, Mendeleev table, you have also to see it in terms of orbital. And you see orbital mean quantum mechanics. So there is really a big relationship between all this theory, what Professor Benius talk about it, and this Mendeleev table, and the hydrogen production, and also fuel cell. So I will go very fast to what physicists understand very well. So let's look, for example, silicon. Silicon have a diamond structure. And you can take one silicon out and make, for example, phosphor inside. This is a substitution of one silicon. And this will give you what we call N-type silicon. And when you form N-type silicon, this means you can put, for every atom, you can put one electron. But if you take one atom gram, this means 6.02 10 to 23 atom, you can have a lot of electron. And this electron with the thermal energy, Kt, they can go from one level, which is already close to the conduction band, can go to the conduction band. And therefore, it's very easy to get this electron for your process. Okay. And of course, there are some theory what you have to know here. First of all, electrons are they are not just everywhere. You have to take into consideration the statistical physics for electron, and there is the probability of occupation of electron, what I made here, and also the density of state of the electron, either in the valence band, for example, in this case here, okay, or in the conduction band. Same if you want to have p-type material. You have to go to Mendeleev table to see which element you can substitute. For example, I just take silicon here, and you take one silicon, you make one bore, so you will have only three. A bore have only 3 electrons in the periphery. So you will, for every bore substitute here, you will have one hole, or one non-electron, or one missing electron. And therefore, your acceptor level will go to the valence band. And of course, here is closed to the valence band, this level of this bore, and therefore you can have a lot of holes in the valence band. So now we create 2 kinds of semiconductor. One semiconductor with it has holes, and one semiconductor with it has electron. And in the 2 cases, either for N-type material, you have physics of the N-type material, or for the p-type material, you have the physics of the p-type material here. For how much electron in the valence band, how much electron in the conduction band, etc. And everything you can calculate it. Also, for holes, the probability, if the probability for electron is 1 over 1 plus exponential. That's the Boltzmann, the statistic, Fermi-Dirac statistic. For the holes, you have 1 minus, because either you have electron or you have no electron. And therefore, the top probability equal 1. Okay. Now, just as a summary here, so one semiconductor is characterized by the valence band with a density of state here, a conduction band with a density of state here. All are semiconductor physics. We can do a lot of, you can all these relation, we can demonstrate it a little bit and find it where it come. And then you can, and here is the Fermi-Dirac statistic, and here is 1 minus Fermi-Dirac statistic for holes. Okay. Now let's go to the compare the all situation. You have the N-type semiconductor, what I represent here, and you have the valence band, the conduction band, the Fermi level closed to the conduction band, and the difference between the conduction band and the vacuum level called the electronic affinity. For the p-type material, the Fermi level is close to the valence band, and you have always electronic affinity, and you have the density of state here, and the donor, the acceptor level is here, close to the valence band, and here is close to conduction band. And now you add to this what happened in the electrolyte. In the electrolyte, we have also density of state. I put it here. And for the occupied or the reduced pieces, if you prefer, and for oxidized pieces. And all the relationship for the N-type material, for the p-type material, and for the electrolyte also. So now what's happened when we make the N-type semiconductor in contact with electrolyte? Because that's how you fabricate an electrolyzer or a photochemical cell with a semiconductor. So because of the electrolyte, because of the Fermi level, and has the Fermi, your material here, your semiconductor, your N-type semiconductor, should have an electronic affinity in a way that electron can go from the semiconductor to the electrolyte. And for p-type, when you make a p-type semiconductor in contact with the electrolyte, your semiconductor, the affinity electronic, has to be in such a way that electron go from electrolyte to the semiconductor. Like if you have two systems, you put it together. In the electrolyte, there is electron. In the semiconductor, there are electron. And when you put it together, you put the system together, it will go to the equilibrium. And at the end of the day, the semiconductor and the electrolyte will have the Fermi level, or the chemical potential, because it's the same name. The physicists call it Fermi level, and chemists call it the electrochemical potential. And then it will be the contact at equilibrium will give you, let's see, will give you the two Fermi level, or the two chemical potential from electrolyte and semiconductor will be aligned. I put here some quits where when you got my presentation, you can try to do exercise for yourself. Here also I put some quits or some exercise, if you like. In French we call it exercise, just to learn a little bit about this stuff here. So I'm not going to, and here also it's think what you can do in exercise. So let's go now to the course. So the 3 slides before, it's some quiz, some exercise where I can give it to the attendee. They are interested to do it in order to learn more. Now let's look. Now, when you make the contact between N-type semiconductor and the electrolyte, and you are in the equilibrium, and you illuminate the semiconductor, what's happened? It's happened the following. That's the semiconductor in the illuminated region, it's not anymore in equilibrium, in quasi-equilibrium. And therefore, it will, the hole and electron, they don't have the same electrochemical potential, or not the same Fermi level. So we will define a Fermi level for electron and a Fermi level for holes. And we will keep the same relationship mathematically, but we have to make a small change. We call the Fermi level for electron Fn and for holes Fp. And because there is when you illuminate, you create electron on hole, holes in the valence band and electron in the conduction band. So there is a kind of delta N and delta P. And if you have a N-type semiconductor, you will have a big car, if you like, or between the chemical potential of electron and chemical potential of holes. And this difference between the chemical potential is the photovoltage, which you can get from your electrochemical cell, your photochemical cell, solar cell. And you see here, for example, what's happened. You illuminate holes, electron go to the conduction band. This means you have to illuminate with energy higher or equal to the band gap. Then because the banding here, and that's why you say you have to choose the electronic affinity of your material in order to have this situation here. And then holes will go to the surface, and they are highly oxidized. They will oxidize water, and the water will be oxidized into proton and oxygen. And of course, we need another electrode. We will talk about it afterward. So what's happened is, and look, please look in this relation here. You have 2 water plus 4 holes in order to have 1 molecule of oxygen. So the water oxidation involves 4 holes, and that's the point. You can't really find easily a material which can have a kinetic to produce oxygen very easily when a reaction needs 4 holes. You have to have what we call a catalyst. That's what we put here in blue here. So the oxygen evolution reaction is one of the key problems for water splitting without applying any voltage, just bringing the delta G, what I talk about, from this splitting of the Fermi level here, or of the electrochemical potential. This is very important. So that's the takeaway here. This we need 4 electrons. This means thermodynamic is not enough. You need some more. You need a kinetic aspect of the problem in order to resolve the problem. Okay. I show you here exactly the same, but with a P-type material. P-type material, you have the Fermi level near the valence band. And when you excite with energy higher than the band gap, what's happened? The holes now go to the bulk, not to the surface, and the electron go to the surface, because the field here, the electrical field in this region here near the surface, is completely the opposite of the other one for N-type, and therefore electron will come here, will meet proton H plus, and then we'll make the reduction into hydrogen. And that's what's happening here. So the first half cell is this one. That's the anode. And the second one, this one is the cathode. So we put it together we have to choose exactly with good parameters the anode. You have to choose with good parameter the cathode, and then you can fabricate a photoelectrochemical cell for water splitting, which just by illumination you can produce hydrogen in the anode. You can produce oxygen in the anode, so you will oxidize water. Then you have as product H+. This H+ will migrate by osmosis, or the gradient of concentration to the cathode. You have to put one membrane in between that only H+ is can move to the cathode, and then in the cathode the H+ will find a lot of electron, and they will be reduced into hydrogen. That's how it's work. Okay. Of course, the problem is extremely complex. If you want to go very, very deep, I just put here this schematic of an electrolyzer with one semiconductor, N-type, and one metal. And you see in terms of charge how it is. You have the drop of the potential you have the semiconductor here, this one here. You have the electrolyte in between, and you have the metal, the cathode. And there are a kind of equilibrium between the semiconductor, the electrolyte, and the other metal. In this situation here, you have to choose exactly the semiconductor, the pH of the solution, and all the parameters in order to have the good photoelectrochemical cell. And the physics of the semiconductor is involved, and the chemistry or electrochemistry is involved. And I just show you here that the light which is coming to the semiconductor will go until a deep, what we call penetration deep, 1/alpha. Then you have the properties of your semiconductor, the minority carrier diffusion length of your semiconductor. And you have this part here, what we call space charge region, where your Fermi level is split into chemical potential for electron and chemical potential for holes. And this is very important. And therefore, you have to be multidisciplinary in order to understand all this stuff here. Okay, now I will show you here the whole system. If you want to build up one electrochemical solar cell where you illuminate your solar cell and you produce oxygen in the anode and hydrogen in the cathode. I just made here a semiconductor N-type, a semiconductor P-type. The N-type semiconductor, this is the reaction will occur there, or what we wish to occur. In the P-type semiconductor, that's which reaction we wish to have. You have a membrane here. This membrane will let the H+ produced in the anode to go through to reach the cathode and to take electron to produce hydrogen. I just put here between the anode and the cathode, you can have a photocurrent, a current. The current is coming from the movement of electron. It's always like this. And I put here one, what you don't know until now is we call a reference electrode. This is, for example, you can have it between the anode and the reference in order to measure the photovoltage here. Or you can put it here between the cathode and the reference to measure the voltage between the cathode and the reference. The reference will give you the voltage. And the voltage, you can make it in the scale, and you have now two scale. One is the electrochemical scale, and the other one is the solid state scale, where the reference is the vacuum level. So if I made some animation here, you can see that you eliminate the semiconductor, both of them, if you want. And it depends on the technology and how you make your device. And then you see that the holes go to the surface. You suppose that you have a good catalyst. And then you produce the produced holes will oxidize water into H plus and oxygen, and the H plus will go to through the membrane to the cathode, and then there they will take electron and to get hydrogen. So if you have 4 H plus, it will give you two hydrogen molecule. That's how it's working. This situation, of course, you see, it's not easy to get. You should have your this redox system of these two half reaction. What we have discussed in the beginning, you have two half reaction. One which happen in the anode, and the other one in the cathode. Have to have their level, their redox level in the right place between the conduction band and the valence band of the n-type. So between the valence band of the n-type and between the conduction band of the p-type. Otherwise, if it's out, it doesn't work. And of course, to have this, you have to have the right material, the right electrode, the right semiconductor, and I show you that the electronic affinity is very important. So you have to choose your material. You have to, otherwise it will not work. Okay, so let's go now a little bit further. I show you here, for example, just one solar cell or photoelectrochemical solar cell with n-type material here, with a metal, a cathode, and the potentiostat here. And potentiostat is a system where it allowed you to apply or to control the potential if you want to make measurement in the lab. And reference electrode, saturated hydrogen electrode. Why saturated hydrogen electrode? Because this kind of electrode can be defined as 0 volt. So it's exactly in the level of the reaction which occur in the cathode. And that's this kind of experiment, you can make it in the lab. I remember when I was teaching in Morocco at the University of Rabat, I did this with a student, and we bought potentiostat. Even we bought a B potentiostat, kind of potentiostat with we work for other thing, and we made students have made their PhD there with a lot of good work. So it was I don't remember Professor Benius. He was in the commission of the PhD of the student, and even I have also 2 habilitation at that time and everything was done in Morocco, and that's very interesting. Okay, so now just a summary to take away. It looks very complicated, but in reality, it's not. I show you here the semiconductor. That's an n-type semiconductor. The black one is in the dark before illumination. And after after illumination, the red one. And you see, as soon as you illuminate your semiconductor, you don't have equilibrium anymore in this region, and you will have one chemical potential for holes and one chemical potential of electron. And in between, that's the voltage what your photoelectrochemical cell will give you here. If it's higher than 1.23 volt, then you can get your your water splitting. And I put here a lot of data which are related to this picture here. And for example, in an exam, for example, for student, I can just give him this picture here, and they say him to find out what it is, that work function, electronic affinity, conduction band, etc. And they have to know this. Okay. So now let's go now to just a little bit more. You have to know that if you have an N-type semiconductor, that's the case here, the majority carrier, for the majority carrier, you have a small change. For the minority carrier, you have a large change for N-type. That's why in this relationship, if you make the logarithm, you put this NC here, so N star over NC, you make the logarithm, and then you have EC minus EFN, and then you can find the value of EFN. Same here, you make P star divided by NV, you make logarithm from the two sides, and then you can find the value of the FP. And then you can calculate the photo voltage, Fn minus FP, that's energy. This means you have to divide by the electron charge, 1.6 10 to minus 19 coulomb, and then you get your photo voltage. So that's, if you want to understand why the Fermi level of electron or the potential semiconductor of electron is just shifted a little bit, but the chemical potential of holes is shifted a lot, then you have to see the physics of semiconductor here. Okay, so you have your electrode in the dark before illumination, and you have it here under illumination. And you have the oxygen evolution reaction on this electrode. Okay, that's for N-type. Okay. Oh. Okay. Now, we're going now to make a little bit of philosophy or to compare what we are doing here to the nature. I think what we have done before to choose one very specific semiconductor, N-type semiconductor, P-type semiconductor, and this semiconductor have to have their valence band and conduction band very well situated energetically in order to have the water splitting. If you compare this to the nature, what's happening in the plant, we have light absorption in our case, and also in the plant, in the nature. Charge separation also, charge transport also. But the nature is doing very, very good this kind of reaction. So they have no problem to make water splitting or to use CO2 of the air to make fuel, green fuel or biomass, etc. The nature do it very good. This means you have to learn how the nature is working. One thing what you have to know also, that the solar spectrum, what I show you here, you have to think about which band gap you have to use. We know that a large band gap is give or deliver a good photovoltage, but low photocurrent. Small band gap material deliver high photocurrent but insufficient or small photovoltage. And I think yesterday, Professor Thomas Hanabil had talked about this very in detail. So you need a tandem material. So you need a combination of material which can take the whole or a big part of the spectrum in order to combine the good thing from material with large band gap and the good thing from the material with small band gap in order to have an efficient device. The other thing is everything happens in the surface of your material, of your semiconductor. And there, for example, if you take CO₂ reduction, it's not just CO₂ reduced to fuel or something like this. It's a lot of intermediate reaction. And there are in the literature plenty of good publication. You can see here one where in order to reduce CO₂ into fuel, you need to go through a lot of catalytic reaction until you get your fuel. So it's not a very easy way. The nature do that very, very easily. But we have to learn from the nature in order to have catalysts which can be easily reduce CO₂, for example, into useful fuel or to split water into hydrogen and oxygen easily. But the problem is here first. At least in first problem is to have enough energy from the sun. Second problem, to have a good catalyst to make either splitting of water or reduction of CO₂. So I'm not a biologist, and I'm not going to stay too much in this, but the nature works extremely good. It's take CO₂ from the air or remove CO₂ from the atmosphere and give you oxygen into the atmosphere. That's a very good thing. And the nature do that in a very, very complicated way. It uses a kind of catalyst, biocatalyst called Rubisco. And there is a kind of mechanism which working in the nature to make this reaction what you see here. Either you take CO₂ plus water what you pump from the here, and you form a glucose, for example, and water and oxygen, or the other reaction around is the aerobic respiration, where you can go from this reaction here and you get CO₂. So the nature, the plant are doing both of them. It's very important, in my opinion. If you want to have to understand things, we have to understand the nature. But this is very difficult. You cannot be biologist, chemist, and physicist. But it's very important, this topic. So let's just make it a little bit very simple. The plant are working like this. The structure of the plant.
You have 5 minutes for the first part, Ahmed.
Okay, thank you very much. So the plant are extremely thinner, 10,000 times thinner than the semiconductor structure. That's one thing what we have to think about. And we can reproduce what happened in the plant in terms for absorption of light and collection of electron hole and etc. Like what Thomas Hanabil have shown yesterday, and that's the Thomas Hanabil proof of concept. He used 3,5 compound. He make a heterojunction between the electrode. He make catalyst from this side, another catalyst from the other side, and he was able to fabricate hydrogen and oxygen with efficiency about 19%. So it's work. but we don't understand everything what the plant are doing. If you like, you can see my habilitation. I don't know if I have made here the reference, but in my habilitation, I talk about this very much. It's in solar energy material and solar cell. So with that, I will stop here. And if you have any questions, just go ahead and ask. I will be happy to answer to your questions.
There are first question.
Yes.
From Mohammed Hilal at 3:30 p.m. Thank you, Professor Ahmed Ennaoui, for all your effort. My question about the possibility of developing the self-sustaining hydrogen energy loop, fuel cells, water, electrolysis, hydrogen fuel cells.
I don't get the questions. Can you repeat it or make it different?
My question about the possibility of developing a self-sustaining hydrogen energy loop, starting from fuel cells and ending at fuel cells, and in between fuel cells, water electrolyzes hydrogen, and hydrogen fuel cell.
Yeah, I understand now. So I think it's very interesting what he says. The problem is people working to produce hydrogen, they are producing hydrogen. That's it. And people are interested to make fuel cell, they are interested to make fuel cell. And I don't believe that there is a company, for example, suppose that we put hydrogen into technology, we put fuel cell into technology, and everything is working. We have just to, I don't believe that a company is able or they have the possibility to make it together. But it's very interesting as a project. I think I advise the attendee is Hilal, you says.
Yeah, Ahmed Hilal.
Ahmed Hilal
But I think, Ahmed, there is some possibility of reverse fuel cell.
Yeah. I know this. But I think what he wants to say that he just
a loop.
Yeah. He just see that we can produce electricity from fuel cell, and we can produce water from fuel cell, and this water, instead of just wasting the water, for example, we can again make it as hydrogen and oxygen. That's what he want to say, is it?
Yeah. A comment from Ismail Abbasi. He said that, but the energy loss could be big, high. I lost the. Excuse me. The comment is that the loss of energy could be high in this loop.
I think the fuel cell, you get a lot of heat from the fuel cell. And this heat, I think you can use it if you want. I don't know what the electrical vehicle are doing when they have heat, how they use it, or they just take it out. But you have a lot of heat and you can use it. In the electrolyzer, you have a lot of heat also. You have seen that you have free energy, you have enthalpy and entropy. And the T delta S is just a lot of heat. And therefore, it's up to the engineer to understand this and to know how to use it.
Another question from Mohammed Al-Malki. Dear speaker, thank you for the excellent and informative presentation. I truly found it very useful and appreciate your unique and engaging way of explaining complex topics. The question is, could you elaborate on the materials challenges in designing catalysts that work efficiently across wide pH range?
That is a very good question, and I'm going to come to this topic at the end, after we have all bases. It's I can do this. You know that is he just asked now the status of research. Everybody is working now on catalyst, the good catalyst for water splitting. We don't have a good catalyst for water splitting. We have platinum. Platinum is a very expensive. We have some material to put with the semiconductor like rhodium. You have seen in the solar cell of Thomas Hannibal, etc. But it's not really a very efficient catalyst. And if they are efficient, if they are cost effective or not, is also a problem. Rhodium is expensive, I guess. And therefore, in the future, the transition metal, for example, what you have developed, the 2D material, can be a solution for this as a catalyst. But I will talk about how people are working on catalysts in order to, there are a lot of different approach. When I'm working, when I go to the measurement, I will talk about this, if you allow.
The second question: how does the density of state in the electrolyte influence the electrochemical kinetic of water splitting?
Yeah, this is, what I have done is just show that it's possible to compare electrolyte or electron in electrolyte with electron in solid. Now, the answer to this question is a question of is empiric for the moment. You actually people take, for example, acidic solution, pH 0, and work with different electrodes and see the result. And then they see in the range from 0 pH to 14 pH. So they don't really care about density. The density of electrolyte is related to the concentration. You have seen it in the relation. And the shape of the density of state had to do with the heat in the electrolyte. If you control the heat in the electrolyte, if you control the pH and the concentration, you will control everything.
Third question: how do the electrode catalysts, typically platinum, perform under real work cycling conditions, and are they promising?
So platinum is very expensive first. So it has to be replaced by another. But it's the only noble metal where when electron or holes are there, doesn't perturb the electrode. And the absorption in platinum is also very well known. So therefore, the advantage of platinum that when you have an electron on the surface of platinum, this electron do only one job, is to give the electron into the H plus to form hydrogen. Doesn't do any other reaction. So platinum is very good, but it's very expensive.
Another question from Sheikh Saliu at 359. What are the main current limitations of nature-inspired technology for solar conversion into green fuels?
So there are many. I think, first of all, you have to collect the spectrum. So you have to make a tandem cell to collect the spectrum in order to have enough electron. That's the limit. And the tandem cell, actually, the only one which is working very good is with 3,5 compound. So to make 3,5 compound together to have a tandem cell is very difficult. So they are able, and as Thomas Hannabel says yesterday, device equal interface. So there are a lot of interface. So if you use 3,5 compound, you have already three interface plus the interface with the electrolyte 2, that's mean 5 interface. And therefore, that's the challenge, is how to collect the whole spectrum. That's the challenge. What is now, and the second challenge is the kinetic. If the kinetic is very slow, then the electron, if they can't go to the reaction, they will recombine, and then you can lose something in the current.
A question from Driss Belkhiri at 358 concern the price and good device of electrolyzer for research prototype at laboratory.
Yeah, I think in the lab, nobody. Okay, it depends what he want to do. If he want to make, I think the best way, and I'm talking about Morocco, I always say this: every university should have what we call workshop, atelier, to make small device. Because if you actually you can buy an electrolyzer, it's not very expensive for the lab. But the best way to do it is to make it in the. You remember in Rabat, we had at the time in the 80. Someone he can make I don't know in German called the glass blazer. So the one he can use glass to make stuff, and you can make electrolyzer in your faculty, just having someone to make a small cell with glass or with quartz, for example. And that's the best way to do it. But if you want to buy it, I think Alibaba, I saw it. You know, there is I'm not making a publicity for Alibaba, but Alibaba or the other in internet, there are Amazon, for example. You can find small electrolyzer for the lab, and they are not very expensive.
Another question from Ismail Abbasi at 4.1. How does the electrochemical reaction temperature affect the cell yields?
Yes, the temperature, and here you can go back to the density of state in the electrolyte. You have to control the temperature in the every movement of the electron make Home effect, which can make heat, and this T delta S in the free in the enthalpy make heat, and this heat can make your cell not performing correctly. So you have to control the heat. That's it. So the best way to really to do science is to make experiment. And we will see how we can do some experiment in the lab, and I think in Morocco, this kind of experiment can be done very easily because it's not really very expensive, and you can get a lot of very good information from. And so I will talk about the action spectra, which is also for normal solar cell, but it can be also for photoelectrochemical solar cell, external quantum efficiency, evaluation of the efficiency solar to hydrogen, current voltage plot and capacitance measurement, etc. I just try to repeat things in order that people can go with a lot of idea, and therefore it's very important to repeat things. Even if I repeat it 2-3 times, it's very good. What I show you here is two things. One is a semiconductor, N-type semiconductor. You see that the semiconductor is in contact with an electrolyte. You see the Fermi level of the semiconductor, and the semiconductor of in the electrolyte are aligned. This means it's in the equilibrium. That's in the dark. There is no light. You see the band edge of the conduction band, the band edge of the conduction band, or of the valence band, and you see here the sparse charge region. Maybe it's time to use a little bit so here, for example, if I make a kind of line here, that we call it the sparse charge region, where the charge is, we call it QSC. And here are charge plus. Why plus? Because you remember before the equilibrium, the electrolyte was here, and the electrons are coming from the semiconductor. Okay, that's why here is charged positively. If we take a p-type, it will be negatively charged. Okay, and you see in the beginning wait a second. Okay, it's not. We'll just lost a lot of time. So the situation in the beginning was here. That's the conduction band here, and the valence. Oh, sorry. And the valence band was here. Okay, that's how it was before the situation. Valence band. Okay, and now after that's the semiconductor and the electrons are in equilibrium, then you have a band bending. Wait a second, I have to go me. Sorry, it's a long time I don't use this. Okay, now it's working. Now, if we go to under the light, that's under the light. The band bending will be reduced because you have holes here and electron here, because electrons are jumping from the valence band to the conduction band, and therefore the band bending became smaller. But there is still a little bit of band bending here. I made the ideal situation. You see here the difference between the Fermi levels. And the Fermi level mean chemical potential of electron. So you have the chemical potential for electron here and chemical potential for holes. And the difference between the two is the photovoltage. I show you here the solar spectrum. The solar spectrum AM 1.5, which is coming until the Earth. And you see that the contrast with the choose of the semiconductor. If you have a semiconductor with large band gap, you will have small. You will have large voltage. sorry for this, large voltage, but small current. If you have this region here, you can get this part of the spectrum. If you have a small band gap, this means in the infrared region, you will have a large current because you have a lot of electron, but small voltage. Okay. And of course, you will have a photovoltage, which is the difference between the chemical potential of electron and chemical potential of holes here. I mean just energy of electron minus energy of holes divided by the charge of the electron. And of course, you have to illuminate with energy higher than the band gap. This means because the hole have to go, the electron have to go from here to here. Otherwise, it doesn't work. Okay. So now you know this. Now we want to measure what we call the quantum efficiency or action spectra also. So what we do is there is a very simple, excuse me. Just want to make a small, okay, now it's work. So we have here the spectrum. The spectrum goes inside a monochromator. A monochromator is a device where you can split, you have some possibility here to have one monochromatic light, one by one. So one of these two mirror here will move in order to go from one wavelength to the other. And then you can have, for example, the red light, the blue light, etc. Okay, this is very easy to understand. And you can have the wavelength in nanometer, and you can translate it in energy. So A is H nu is Hc over lambda. H is the Planck constant, and C the velocity of light. Okay. So you can have light here coming to your electrode, and you can you know that the light is depend of which wavelength. You see here the spectra is not just one line. It's for every wavelength there is an amount of photon. It's a flux. Okay, so that's why I wrote a P function of lambda. Okay, the current what you get also will be function of lambda because this. So this is a electrochemical cell. That's what you can, for example, buy very easily. It doesn't cost very much. It's a very good configuration because you have a possibility to make water going inside and going out, the cold water. So you will control the heat, as I told you before. So inside you have three electrodes: a working electrode, a reference electrode, which is a reference electrode, a working electrode, which is your semiconductor, and a counter electrode, which can be the platinum. So you have two electrodes. So here I showed the schematic in another way. You have the reference here, for example, hydrogen. You have the semiconductor, the photoanode, and you have the platinum, for example, as counter electrode. Okay. And you can use a potentiostat, which control the potential. So you can measure your potential. Very good. So if you make the ratio of the number of electrons which go through the circuit, this means you have a hole in the electron. The electron doesn't recombine; it's are collected and go through the circuit. and are measured in your potentiostat. Then you take this current, the photocurrent, you divide it by the charge of electron, and you have the number of electrons participating to the photocurrent. Then you take a pyranometer or whatever, a detector, which measure the flux of the intensity of your light of this M1.5, and you can know exactly by dividing the intensity of light by h nu, h c over lambda, you can have the number of photons which is incident on your cell. And the ratio of these two, that's the quantum efficiency. That's the quantum efficiency, the ratio of these two. And this is very important. Here, I don't take into consideration the chemical reaction. I just do like a physicist measuring the quantum efficiency of a solar cell for the moment. Afterward, we will see how to manage this for our case. But that's how a quantum efficiency is measured. And we call it external quantum efficiency because we don't measure the reflection. You know, if I look, I just make, for example, this light which is coming to the electrode, it will be some light can be reflected. So the some light P of lambda divided, multiplied by R, the reflection coefficient is reflected. So it's not usual for the cell. That's why we call the external quantum efficiency. If you want to have internal quantum efficiency, then you have to correct your external quantum efficiency with the reflection. Okay? So that's how we can measure the external quantum efficiency for a solar cell or for an electrochemical solar cell, whatever. Again, the same, I make it here. So that's what I show you, what we have just explained. And there is something what we call action spectra or spectral response. Spectral response. And this is just the ratio of the photocurrent divided by the light. This is also when you buy any device, sensor or solar cell, they don't give you the quantum efficiency, they give you this parameter here because they don't want to spend too much time to make this calculation here. But you have to do it in your lab, the quantum efficiency. So if I take this relation and just put some calculation, which is very easy, you will find that your external quantum efficiency and your action spectra or spectral response are related by this quantity here. And this quantity here is just when spectral response equal 1. That's why we call it spectral response maximum. Okay. And of course, there are a lot of work done when we compare what's happening in the nature and what's happened in the lab. And you can just try to think about it by comparing the photosynthesis here and when you put together semiconductor, for example, here. I have shown here two semiconductors, one here in type 1p type, and are together, and there is in between a contact, and you can make, for example, you can simulate what's happened in the nature like this. Okay. So here is the setup, complete setup. When I came to Germany in 1983, the first thing what they asked me to do is to set up this, to buy everything and to make it. It cost a lot of time, but I did it. So how it's work? You have the light source here. You have a monochromator here. Monochromator will deliver monochromatic light. You have a shopper. A shopper is a kind of, I don't know how to call this. You have some window, and then when it's turning, you get a signal like this one, like the signal here. Okay, because there are stroboscopy. That's the, in French, we call it like this. And then I put here a beam splitter. So one part of the light go to your cell, and one part of the light go to your detector here. Either a pyranometer, which is very expensive but very good, or a silicon detector if you have a very good silicon detector where you can control the temperature, for example, and you have the data from your silicon detector, and you can also use it. So you can measure the current of your cells, and you can, of course, be in a lab where everything is controlled. You can make water here coming inside between the two. You see, you have a double glass here, and so you can control the temperature because the water is coming in and going out, and then you can have a 25 degrees because you want to work in standard condition. You have the 3 cell, the 3 electrode, the working electrode here, a counter electrode, and you can have a reference electrode. So you can measure, for example, your current, and you can measure also the current through your detector, which is very well known. You have the whole data in your software from your detector. Before you do this work, for example, you can see for different detector there are the axion spectra of different detector, or the quantum efficiency of a different detector here. Okay, so you have the solar spectrum here compared to other detector, and your signal can go through a EEE, for example, here to a lock-in, and this signal here from the light, from the shopper can go also inside, and your lock-in or the synchron detection can take, for example, the dark current, the current in the dark of your cell, plus the photocurrent of your cell, and select only the photocurrent with the phase here, because your lock-in is enough intelligent to see that when there is a light and where there is no light. So he can make a difference between dark and light, and then he give you, for example, only E versus lambda. So that's how it works. So that's a setup which you can, I think, I advise my colleague in Shuaib to Cali University to make this kind. This is a good work for engineer. If someone will have a diploma engineer, he can build up something like this, a little bit more sophisticated with intelligence artificial for artificial intelligence, and they can do this kind of job. So that's what I wrote here everywhere. So now, saying this, how to make the measurement? You just make a table here. That's the best way to make the measurement. That's how I did it long ago. You choose your monochromator. First of all, you have a spectral response, which is known for your detector here, a silicon detector, or better to have a detector where you have a different semiconductor. And each semiconductor is working in the range, in one range in the spectra M1.5. Okay, and this you know it. You put it in your software. That because when you buy this, they give you the characteristic, and you can have it in ampere per watt. Okay, how much ampere will give you how much watt from the light? This is known. And then you try to make this kind of table, and this you will not do it by hand. Your computer and your software will do the job, and then you will have your second, which is not known, and then you can just make a small report of both of them, and then you can get this here, the spectral response of your solar cell, if it's a solar cell, or your electrochemical solar cell, if it's electrochemical solar cell. And of course, as I show you from one relation that here I brought it here, that there is a relation between the external quantum efficiency and spectral response. So you can get your external quantum efficiency like this. I advise you, when you have time, I will give my presentation in PDF to my colleague in Morocco, and you can try to make this kind of calculation, which is easy, but you know, students sometimes they are lazy to do application, and but if they are in the exam, they have some trouble to do it. So therefore, it's good to know how to work, for example, with atomic scale numbers. You see the charge of electron, etc., and then to find 1 nanometer equivalent to 10 to minus 9 meter, etc., to find a relation like this. So that's very important as a quiz. So you can plot your spectral response versus lambda, for example. And you can see a lot of good things. For example, you can now, I made it here by lambda and here with energy. And you know the lambda and energy, they have a relationship here. And if you write this relationship in electron volt and nanometer, you have a very well-known relation. Energy in electron volt is 1239, 1239 divided by lambda in nanometer. See exactly the same relation, but in atomic scale here. So you can see your onset of the current. You can see if there are some recombination at the surface here, etc. So it's very, very important, the spectral response, and also the quantum efficiency. I show you here one work what I have done when I made my habilitation here in Germany. You can find it here in this article. It's 100 page, this article here, what I published in solar energy material and solar cell, where you find a lot of information here. Okay, so that's the pages here. So it's a lot of work. Okay, so you can see here I plot the external quantum efficiency, and we can see the band gap of the material. That is a material what I call FAS2, iron disulfide. I developed this material by myself from the beginning, and you can see here the quantum efficiency. You can see here there are some recombination, because normally it should be quantum efficiency should be like this, but you have a lot of loss, so you have to explain all this. Okay, here, if you want to correct your external quantum efficiency to have internal quantum efficiency, by measuring the reflection. Then you have to use, for example, this kind of experiment where you put your sample here, and then you have an integrated sphere here and a detector or a spectrometer, and you can measure for every wavelength the reflection. Okay, and then you can correct your external quantum efficiency to get internal quantum efficiency. And of course, logically, you will have 100%. I just put here one example from the literature, from a paper from Zhang, Zhang in Energy 2019, where he showed, for example, for silicon solar cell, the importance of anti-reflect coating here. So it's and here is the reflection. So it's that's, you have now action spectra. You know how it is. You have an external quantum efficiency and you have internal quantum efficiency. But until now, I just made this without talking about electrochemical solar cell. Now, if I want to really to do things very properly, I have to take into consideration that hydrogen evolution reaction require 2 electrons per hydrogen molecule, because this, meaning 2 photons. So we have talked about the number of photons for 1 hydrogen molecule. This means our formula will be like this to measure the external quantum efficiency, not the one only without this number. So there is a difference when you are measuring a solar cell, solid state solar cell, like silicon, like every solar cell. And if you are measuring the external quantum efficiency for photoelectrochemical solar cell. Okay, so here I take one example. For example, and this is, you can take it as a quiz if you want. So you have a 50 milliwatt light with a laser maybe, and then incident photon characterized by this energy. This means this wavelength, and that's the diameter of the area of your light, incident light. So you have everything to measure with your detector. And then if you make the calculation of the energy here, you look how much photon you have in the flux, and you convert it into joule per photon, and you consider that your material is a ideal gas. You know, you have a relation you learn at the university, PV equal N number of atom or molecule in the gas, like this. So you have an ideal gas. Then you can make a calculation, and at the end, you can find this external quantum efficiency. So here is like an experiment where we suppose that we have we have this value here. That's what we have measured. And we consider our gas, hydrogen gas, like ideal gas. And then with this calculation, you can find the external quantum efficiency. So if you take these two, it's not the same. Huh? Therefore, the external quantum efficiency or the quantum efficiency for a solar cell is one thing, but if you are working with a electrochemical solar cell, then not all electrons coming to the surface will participate to the production of hydrogen. And therefore, you have to be very careful. Okay. This is This is a setup where you can make, for example, cyclic photometry. This means you can apply to your electrode potential V time versus time, and you can measure the current, and to see where is the production of hydrogen and production of nitrogen. Okay.
Ahmed, you have 5 minutes.
Oh la la. So let's see, just explain this curve here. That's what you can get from cyclic voltammetry. So you have in the dark and under the light. And you see here, I just show you how I have to go back. You see here the role of catalyst in your solar cell. So when you make the light, if you have a very good catalyst, then you can see the onset of your photocurrent very early here. Your photocurrent come very early, which correspond to the oxygen, to the hydrogen, pardon. And then you can, if you have a very bad catalyst, then the kinetic is very bad, and that I come back to the questions of one of the audience, that the catalyst improve the current of the onset of the current. So you gain. You see here that the good catalyst here, this good catalyst, show that you get 10 milliamp per square centimeter just with 100 millivolt here. So in contrast, you need 600 millivolt in order to produce exactly the same. And therefore, for the production of oxygen, you need really a good catalyst in order to make your reaction. Okay, I think I will show you here the conditions. Oh, I'm very sorry for that. Yeah, so you see, I just show here a platinum or a counter electrode, and that's the level of the work function of the metal of the counter electrode. And I show you here the N-type semiconductor. And you see the two level here, the level of oxygen, of hydrogen evolution, and the level of oxygen evolution. Here there is a mistake. That is up H plus H2. Not. And you see the two level here in between is 1.23, should be between the conduction band of your N-type material and the valence band of your N-type material. And your metal should be in the right place for the hydrogen evolution. So you need this. You need first the band gap has to be larger than this 1.23 electron volt. That's the first. Secondly, the voltage you can develop here should be also higher than 1.23 volt. This means the recombination is not critical at the interface. And the conduction band edge here, this one, be above the electrochemical potential, this one here. And the valence band edge should be below the other one. So that's conditions which if you want to see some hydrogen production. Okay. Unfortunately, we don't have very much time, but I'll try to explain this because it's very important. So that's how you can calculate or measure the efficiency of hydrogen. This 19% what Thomas Hanabil have shown you yesterday is measured like this. So you have the rate of hydrogen production here, this number here. And this you can measure with mass spectroscopy, for example. You have this free energy here. This it's delta G, not G. And that's divided by this AM 1.5 watt per square meter. That's the solar spectrum. And that's the efficiency solar to hydrogen. So again here, written very explicit. That's the rate which you can measure. That's the value, the minimum energy you need for water splitting. And that's the, here is the AM 1.5. Okay. But we can introduce another formula which is more interesting, which this one here, where you see that you have the electrode surface. It's very important. You have the current, the photocurrent. And you have this, the value of voltage, 1.23 volt. And you have something called the Faradaic efficiency. And the Faradaic efficiency is the measure of the selectivity of specific electrochemical product. So this formula is very general, very important. If you want to do one experiment, one chemical reaction, hydrogen production, reduction of CO₂, etc., the Faradaic efficiency is very important. And you can see in the literature, in the publication, how we can measure this Faradaic efficiency. Of course, this Faradaic efficiency will depend also on the kinetic. But this I will not talk about it now. I just want to show you here how to do some measurement. For example, here, for example, you have the hydrogen, the efficiency of hydrogen. I think I got Sharaf. Please give me 5 minutes. So that's the efficiency, and we can really combine the calculation and the experiment to get the value of hydrogen production. I'm not going to go to this. So I think it's better if I stop here, because we don't have time for all this stuff. Of course, if you know all what I have said here, then you have to start research. And in research, in order to know which catalyst is very important, there are many possibilities like volcanic float, etc. Yes. So I will stop here. And I hope that you learn something from my talk, and thank you very much.